China just tested a 6G signal that hit speeds over 100 times faster than 5G, and it happened so fast that most of the world did not even see it coming. In one single second, they moved 1 trillion pieces of data straight through the open air. No cable under the street, no fiber wire buried in the ground, just a beam of waves cutting through empty space like nothing was even there. 1 trillion bits in 1 second has a name. It's called a terabit per second. If that number doesn't mean much yet, here's a way to picture it. Take 20 full-length movies, all in crisp high definition, and imagine every single one finishing its download before you even finish blinking your eyes. That is roughly the scale we're talking about, not a rough guess pulled out of thin air. Actual, measured, published science that other researchers checked and confirmed. Here's the part that should really grab you. This was not some flashy demo built to impress a room of investors for 5 minutes and then quietly vanish. This is one piece of a much bigger race. A race to build the network that eventually replaces the one your phone is using right now. And whoever wins that race doesn't just get bragging rights. They get to shape how phones, cars, hospitals, and entire factories talk to each other for the next 20 years. So how did anyone manage to push that much information through thin air without it falling apart halfway there? And why should any of this matter to you, sitting right where you are, holding a phone that already feels plenty fast? Stick with me, because the answer runs through a part of the radio world that scientists tried and failed to use for decades. A problem that looked impossible to fix, and a fix that came from a direction almost nobody expected. Section 1, the number that shouldn't be possible. Let's slow down on that number for a second, because it deserves it. Right now, a really good home internet connection gives you something close to 1 gigabit per second. That already feels fast. You can stream 4 different shows in perfect quality at the same time and never notice a slowdown. Most people never even come close to using all of it. A terabit is 1,000 times bigger than a gigabit. Not 10 times, not 100 times, 1,000 times. So if your home internet is a garden hose filling up a bathtub, this new wireless link isn't just a bigger hose. It's closer to a fire hydrant blasting straight into a swimming pool. The jump in scale is not even close to a fair comparison. The team behind this result works out of Beijing University of Posts and Telecommunications, alongside researchers from Xi'an University of Posts and Telecommunications. They built a system that pushed data through open air at 1 trillion bits per second. And they didn't stop at doing it once under perfect lab conditions with everything lined up just right. They did it across a real distance, roughly 50 meters, which is about half the length of a football field. They used a clever mix of light-based signals and radio-based signals working as a team, each one covered for the other's weaknesses. And then they published the whole thing for other scientists around the world to check, question, and try to poke holes in. That last part matters more than people realize. In science, a claim that can't survive other experts trying to tear it apart usually falls apart fast. This one didn't. It held up. Let's put the raw math side by side because it makes the gap even clearer. At a normal home internet speed of 1 gigabit per second, downloading a 2-hour movie in high definition takes somewhere around 12 seconds. Not bad at all. At 1 terabit per second, that same movie finishes before you've even finished reading the sentence. We're not talking about a slightly faster version of what you already have. We're talking about a different category of speed entirely, the kind that used to only exist in research papers about the distant future. And here's something else worth noticing. This test wasn't done inside some perfectly sealed, climate-controlled chamber with every variable locked down. It happened across a real open distance, with real air, real moisture, and all the messy conditions that come with testing something outside a lab. That detail matters a lot, because plenty of exciting technologies look amazing in a lab, and then quietly fall apart the moment they meet the real world. Around the same time, a separate research effort set up what's being called the world's first working trial network for this next generation of wireless technology. It was built in Huairu, a district just outside Beijing. That live network also hit peak speeds close to 1 trillion bits per second. But here's the detail that almost got buried under the flashy speed number. The delay between sending a signal and it actually arriving was incredibly small too, way smaller than anything your phone deals with today. We're going to come back to why that tiny gap matters so much, because it might actually be the bigger story hiding inside all of this. And this isn't just about your phone loading pages a little faster either, even though that's the easiest part to picture. We're talking about the kind of speed and responsiveness that self-driving cars need to actually trust each other on the road, that hospitals need to run remote surgery without a dangerous lag, and that entire factories need to run thousands of coordinated robots without a single one falling out of step. Your phone is just the most familiar example of a much bigger shift happening underneath it. Here's the thing though. None of this happened by accident, and it definitely didn't happen overnight. To understand why this number is such a huge deal, you first need to understand a problem that's been quietly building for years, one that almost nobody outside the telecom world has noticed yet. There's a wall coming, a real one, and the current network running your phone is already close to hitting it. Before we get into that wall and how these scientists found a way around it, if this is the kind of story that gets your brain turning, go ahead and hit subscribe right now. Not because every channel out there asks for it, but because this particular story keeps getting stranger the deeper you go. The next part covers a piece of the radio world that scientists tried to use for decades and basically gave up on, and the fix for it is one of the more clever engineering tricks you'll hear about this year. You'll want to see exactly how they pulled it off. Section 2, the wall nobody talks about. Here's something most people never stop to think about. Every phone call, every video you stream, every text you send travels through the air as a wave, and waves need room. Actual physical room, in a very real sense. Think about a busy highway. And when there are only a few cars on it, everyone drives fast and smooth. Pack that same highway with 10 times as many cars, and suddenly everyone crawls along, bumper to bumper, going nowhere fast. Wireless networks work almost exactly the same way. Every device around you right now, every phone, every smartwatch, every security camera, every little sensor in a nearby factory is another car on that same crowded highway, all trying to use the same lanes at the same time. Every single generation of wireless technology has run into this exact same wall eventually. The first generation could barely handle a phone call without static. The next couple of generations added texting, then basic internet, then finally enough speed to stream video without endless buffering. Each time, the new generation felt unbelievably fast the day it launched, and each time, within a handful of years, it started buckling under the weight of everything people and machines wanted to do with it. 5G was simply the newest chapter in that same repeating story. 5G was supposed to fix this, and for a while it genuinely did. It's a seriously impressive piece of engineering when you look at how it actually works. It uses a clever trade-off, medium-sized waves, that can carry a solid amount of data while still traveling a decent distance. Instead of a few giant towers covering huge areas, cities built thousands of small towers packed close together. Picture swapping a handful of massive floodlights, lighting up a stadium for thousands of small, precise light bulbs spread across every row instead. You get better coverage, less wasted signal, and a much smoother experience overall. The scale of that rollout is honestly hard to wrap your head around. By the middle of the 2020s, more than half the people on Earth had access to 5G coverage. China alone built more than 4 million 5G towers. By the end of 2024, over 550 million people in China were connected through just one single carrier. That kind of build-out doesn't come cheap either. China Mobile, just one of the country's telecom companies, reported spending more than $3.5 billion on its 5G network in a single 6-month stretch. That's the kind of money usually reserved for building entire cities, poured instead into invisible lanes in the sky. Factories started using 5G to run robotic arms with barely any noticeable delay. Hospitals used it to send live video feeds between operating rooms across entire cities. Busy shipping ports used it to guide massive cranes and containers without a single physical cable connecting any of the machinery. It quietly became the backbone that modern life now runs on, without most people ever thinking twice about it. Here's a simple way to picture what spectrum actually means, since it's a word that gets thrown around a lot without much explanation. Imagine the sky is covered in invisible lanes, kind of like a highway you can't see. Every wireless signal your phone calls, your video streams, your smart doorbell has to squeeze into one of those lanes. There are only so many lanes to go around, and every single year, more devices show up wanting to use them. But here's the problem. Nobody put on the marketing posters. A single 5G tower can only reliably handle so many connected devices before performance starts dropping off, usually somewhere around 1,000 devices before things get shaky. That sounds like plenty until you actually do the math on a crowded place. A packed stadium during a big game can easily hold 60,000 phones, all trying to post, stream, and text at the exact same moment. That's 60 times more devices than a single tower is built to comfortably handle, all crammed into one building on one afternoon. Airports during a holiday rush run into the exact same wall. So does a factory floor covered in thousands of tiny sensors, all trying to talk to the network and to each other at the exact same time. Suddenly that highway is jammed solid and everyone is stuck sitting in traffic, waiting their turn. Then there's the other problem, the delay. That's the tiny gap between a device sending a signal and getting a response back. On 5G, that gap sits around 0.004 of a second. For streaming a video, that gap is basically invisible. Your brain can't even register something that fast. But for a self-driving car trying to react to a kid suddenly running into the street, or a robotic arm in an operating room being controlled by a surgeon hundreds of miles away, 0.004 of a second can be the difference between a routine moment and a genuine disaster. Engineers have a blunt way of putting this. 5G was built for people scrolling through apps and watching videos. It was never really built for machines that need to make split-second decisions completely on their own, thousands of times every second, with no human anywhere near the controls. And here's the frustrating part. You can't fix this by simply building more 5G towers. That's like trying to fix a traffic jam by adding more lanes to the exact same overcrowded highway. Eventually, you just run out of room to expand. What you actually need isn't a bigger version of the same road. You need a completely different road, built from scratch, in a place nobody had figured out how to safely build on yet. So where do you even find room for a brand new road when the sky already feels this crowded? To understand how, we need to look at one part of the radio world that almost every engineer on Earth had quietly written off as a lost cause. Section 3, the frequency. Everyone gave up. On somewhere between the radio waves your phone uses today and the light your eyes can actually see, there's a stretch of the spectrum called the terahertz band. For a long time, almost nobody wanted to go near it. The name itself just describes how fast these waves wiggle back and forth. A terahertz wave vibrates about 1 trillion times every single second. That's so fast it's honestly hard to picture, but the important part is simple. The faster a wave wiggles, the more information it can carry packed inside it. Kind of like how a faster drummer can fit more beats into the same 1-minute song. Here's why that matters. Terahertz waves can carry a genuinely enormous amount of data, far more than the waves your phone relies on right now. Think of the difference between a narrow country road and a 20-lane superhighway stretched out in front of you. In theory, this part of the spectrum could move almost unbelievable amounts of information all at once. But there was a catch, and it was a brutal one. These waves are incredibly weak travelers. The moment they leave an antenna, they start getting soaked up by something you'd never expect to be a problem, ordinary water vapor floating in the air around us. It's like trying to shout across a room that suddenly fills with thick fog. Your voice doesn't carry, it just gets swallowed up within a few feet, no matter how loud you yell. For decades, research teams all over the world tried to work with terahertz waves, and one group after another ran into that exact same wall. The signal would basically die seconds after leaving the device. A brilliant idea on paper, practically useless the moment you tried to use it outside a sealed lab. Most teams eventually gave up and moved on to easier problems. It's worth pausing here to appreciate just how many smart people had already tried and failed at this exact problem. This wasn't some obscure corner of science nobody had thought to explore. Universities and companies around the world spent years chasing terahertz communication, publishing papers, building prototypes, and running into the same invisible wall over and over again. Some of those prototypes worked, technically, but only inside rooms with the humidity carefully controlled down to the last percent, hooked up to cooling systems the size of a small refrigerator. The moment you tried to take any of it outside, into a normal city with normal weather, it fell apart within a few steps. That track record is exactly why this next part is such a big deal. This is where the story actually gets interesting, because instead of walking away, a handful of research teams in China decided to attack the problem from a totally different angle. Instead of trying to make a terahertz wave travel further all on its own, what if you could keep boosting it and steering it the entire way there, constantly, in real time, adjusting for exactly how much the surrounding air was soaking it up at that exact moment? Picture a firefighter holding a hose in strong, shifting wind. If they aim it once and just hold still, the water sprays everywhere except where they actually want it to go. A skilled firefighter constantly makes tiny adjustments instead, correcting for every gust as it hits. That's basically what these new antennas do, except instead of correcting for wind, they're correcting for moisture in the air, thousands of times every single second, faster than any person could ever react. The antennas themselves are honestly wild once you look closely. Each individual piece is smaller than a single grain of rice, and thousands of them get packed onto one chip roughly the size of a postage stamp. Instead of relying on one antenna blasting a signal in a straight line and just hoping it survives the trip, you get thousands of tiny antennas working together like a swarm, constantly reshaping the signal on the fly to punch through whatever the air throws in its path. Think of it like a colony of ants carrying a heavy leaf back to their nest. No single ant is strong enough to carry it alone, but working together, constantly adjusting their grip as the ground shifts under them, the whole group gets it there anyway. That single shift, from one dumb antenna blasting in a straight line to thousands of smart antennas adjusting together in real time, is what let the signal survive a trip that used to kill it within a few feet. This exact kind of engineering is what powered that record-breaking test in Beijing, the one that pushed 1 trillion bits per second across roughly the length of half a football field. It's also what made that trial network out in Huairou possible, the one hitting similar speeds with almost no delay at all. Other teams have been chasing the same goal from different angles too. Researchers connected to China Mobile, along with teams from Southeast University and Fudan University, have run their own experiments using this frequency, some hitting real-time speeds above 100 billion bits per second, with a few tests running 2 signals at once to push that number even higher. Huawei's research team has been exploring a slightly different use for the same frequency. Instead of chasing raw speed, they built a system that uses terahertz waves almost like a form of radar. It can send a wave through a sealed box and figure out exactly what's inside without ever opening the lid, just by reading how the signal bounces back and changes shape. That might sound like a neat party trick at first, but stretch that idea out, and the uses start to pile up fast, spotting a hidden crack or defect on a factory line in real time before a product ever ships. A new kind of medical scan that checks the human body without using any radiation at all. Even checking food for contamination before it reaches a store shelf, or spotting pollution in the air over a city. One frequency, doing double duty as both a superfast messenger and a set of eyes that can see through things ordinary cameras can't. There's another piece of this puzzle worth mentioning too, because it shows this isn't just one single trick. It's a whole direction the country is pushing in at once. Chinese researchers, working with a satellite program called Jilin-1, have managed to beam data between a satellite in orbit and a truck sitting on the ground at speeds around 100 billion bits per second, using a focused beam of light instead of a traditional radio signal. It's a different piece of technology aimed at a similar goal, moving huge amounts of data through open space without needing a single physical cable anywhere along the way, whether that's through the air near the ground or all the way down from orbit. Let's circle back to that other number from earlier, the one about the delay being almost nothing in that Huairu trial network. This is where things start to feel less like a science fair project and more like something that could actually change daily life. A gap of just a fraction of a millisecond is fast enough for 2 self-driving cars approaching the same intersection to silently work out who goes first and react before a human driver would even notice the other car was there. It's fast enough for a surgeon in one city to guide a robotic tool inside a patient hundreds of miles away and actually feel like their hands are right there in the room, instead of fighting against a tiny but dangerous lag. Speed alone gets you faster downloads. Speed paired with almost no delay gets you machines that can trust each other enough to move and react together, like a group of dancers moving in perfect sync without ever needing to look at each other first. Here's what actually separates all of this from earlier attempts at using this frequency. It isn't that scientists suddenly discovered terahertz waves out of nowhere. People have known about this part of the spectrum for a long time. What changed is that someone finally found a practical way to keep the signal alive long enough, cheap enough, and small enough to actually build into real devices instead of leaving it stuck on a lab bench the size of a refrigerator, surrounded by cooling fans and cables. And that shift, moving from a cool science experiment to something you could actually manufacture and sell, is exactly what turns a lab result into something that could eventually change how your phone, your car, and your hospital all talk to one another. But a single successful lab result is never the whole story, no matter how impressive it looks on paper. The real question was always going to be whether the rest of the world takes this seriously enough to build on top of it. And it turns out that part of the story is even bigger than the lab result itself. Section 4, a race nobody can afford to sit out. Here's where this stops being a pure science story and starts turning into a global chess match. China didn't just publish one impressive result and call it a day. The country started serious research into this next generation of wireless technology back around 2019, earlier than most other major countries even began paying close attention to it. Since then, Chinese researchers and companies have filed more than 13,000 patent applications tied to this technology, which works out to something close to 40% of every single patent filed on this topic worldwide. Huawei alone holds more than 3,000 of those patents. China Mobile, the massive state-backed telecom company, holds close to 2,000 more on top of that. Why should a patent count matter to someone who just wants their phone to work better? Because whoever holds the core patents on a new technology often ends up shaping how that technology gets built everywhere else on the planet, whether other countries love that fact or not. Think of it like being the first person to design the shape of a power outlet. Once enough countries build their walls around your design, everyone else who wants to sell an appliance there has to build their plug to match it, forever, or at least for a very long time. It happened with earlier generations of wireless technology too. Whoever writes the first widely adopted blueprint tends to quietly set the rules everyone else eventually has to follow, simply because so much of the early hardware and software gets built around their version first. You might be wondering why any of this should matter to you personally, since you're not exactly filing patents or building cell towers in your spare time. Here's the honest answer. The country and companies that win this race get to decide which chips end up cheapest to manufacture, which features show up in phones first, and which places on Earth get access to this speed early versus years later. It's a bit like watching a handful of companies quietly decide the shape of the next decade of technology, long before any of us get to vote on it with our wallets. China's push here didn't start with wireless towers either. It started even further out than that. Between 2020 and 2024, the country launched a string of test satellites specifically built to explore this next generation of communication technology from orbit, making it the first country to run that kind of test at all. That's the same pattern you see across this entire effort. Start early, test in multiple directions at once, ground-based labs, satellites, factory floors, and let whichever approach works best lead the way forward. China's government has already published a detailed roadmap laying out its plans for this technology, aiming for real commercial rollout by the year 2030. That might sound far off, but in the world of building entire national networks from the ground up, factories, chips, towers, phones, 2030 is actually right around the corner. None of that gets built overnight, no matter how good the lab results look today. And China is far from the only country racing toward this finish line. In early 2024, 10 countries, including the United States, France, South Korea, the United Kingdom, and Japan, signed an agreement laying out shared basic principles for how this next generation of wireless technology should be developed going forward. The message underneath that agreement was pretty clear, even if nobody said it out loud. Nobody wants to be the country still holding an outdated network while everyone else has already moved on to something faster and better. Other breakthroughs have been popping up outside China too, which tells you this definitely isn't a one-country story, even if China currently looks like it has a head start on this particular piece of the puzzle. In late 2024, researchers in the United Kingdom set their own wireless speed record, using a system that blended several different types of wireless signals together instead of relying on terahertz waves alone. Their setup averaged close to 940 billion bits per second, fast enough that a 2-hour movie in crisp 4K quality, something that would take almost 20 minutes on a typical 5G connection, finished downloading in about a tenth of a second instead. Different approach, different country, but strikingly similar destination. Teams in Japan, South Korea, and across parts of Europe are all chasing different pieces of this same puzzle right now too, sometimes racing each other directly, sometimes quietly, comparing notes behind the scenes. There's also been steady progress on a slightly different but closely related front. Engineers in China recently unveiled a new kind of chip that can smoothly switch between several different types of wireless signals, everything from the ones your phone already uses today, all the way up to this new high-frequency terahertz range, all inside one single tiny component, barely bigger than a fingernail clipping. Switching between those different signal types used to require completely separate chips bolted together inside a device. This one chip can flip between them in under 200 millionths of a second, hundreds of times faster than the blink of an eye, and still push single-channel speeds faster than 100 billion bits per second while it does it. For anyone trying to actually build a phone that can use this new technology someday without making that phone bulkier or more expensive, that's a genuinely big deal. Here's the part that really puts everything into perspective. When one piece of technology can pack 12 times as many connected devices into the same amount of space, while cutting delay down to a level that's faster than human reflexes could ever manage, that's not a small upgrade, sitting quietly in some engineering journal. That's the kind of gap that forces every serious company in the entire industry to pay close attention, whether they wanted to or not. None of this stayed quiet behind closed doors either. Major telecom industry conferences that used to treat this frequency band as a distant, decade-away curiosity have spent the last couple of years suddenly putting it front and center on the agenda. That kind of shift doesn't happen because of a flashy press release. It happens because the people whose actual job is building these networks looked closely at the data and realized the timeline had just moved up faster than anyone expected. A rollout like this almost never happens as one single flip of a switch across an entire country. It happens in pieces, one crowded district at a time, usually starting in places where the payoff is biggest and easiest to prove first. A factory that needs thousands of sensors talking at once. A hospital campus that needs rock-solid connections between buildings. A busy stretch of a major city where regular networks already struggle every single day. Those are the places most likely to see this technology first, long before it ever reaches a quiet neighborhood or a small town. So if the science genuinely works, and the whole world is scrambling to build on top of it, does that mean this technology shows up in your pocket next year? Not exactly, and being honest about that part matters just as much as being excited about the breakthrough itself. Section 5. What actually happens next? Here's the honest part of the story, the part that doesn't usually make it into the flashy headlines. Terahertz waves still can't punch through thick walls the way the signals your phone uses today can manage without much trouble. Heavy rain can weaken them significantly too. That means for years, maybe longer, this technology will likely work best in specific crowded places rather than blanketing an entire countryside the way older networks were built to do. Think packed stadiums, busy airports, crowded factory floors, and dense city blocks. not quiet farmland or long stretches of open highway. There's also a manufacturing problem that doesn't get talked about nearly enough. Building millions of those tiny rice-sized antennas reliably and cheaply enough to sell is genuinely hard. Early production runs have run into real quality issues, with a meaningful chunk of chips coming out not good enough to actually use. That's a completely normal part of scaling up any brand new kind of hardware for the first time, but it's also a real hurdle, standing between an impressive lab result and something you can actually walk into a store and buy. On top of that, countries haven't fully agreed yet on exactly which piece of the terahertz band everyone should use, or how. If that doesn't get sorted out carefully through international cooperation, you could end up with a messy situation where a device built for one country's network doesn't work properly the moment you cross a border into another one. That's not a hypothetical worry either. Earlier generations of wireless technology went through their own messy, split-up years too, where different regions of the world built around different versions of the same basic idea, and it took real time, real negotiation, and more than a few frustrated engineers to eventually get everyone speaking the same language again. That agreement, 10 countries signed back in early 2024, the one built around shared basic principles, exists specifically to try to avoid repeating that same mess this time around. Whether it actually works is still an open question. Good intentions on paper and smooth cooperation in practice are two very different things, especially when so much money and national pride are riding on who ends up ahead. If you're wondering when any of this actually reaches an everyday person walking around with a regular phone, the honest answer is probably not for a while. Most researchers in this field point toward the very end of this decade for the first real commercial versions of this technology. And even then, it will likely show up first, as an extra feature layered on top of existing 5G networks in specific busy locations, not a full replacement overnight. The phone in your pocket right now will probably still be perfectly fine for a good few more years yet. So here's the honest bottom line. The core science genuinely works. That part is settled, and it's already been checked and rechecked by outside researchers who had every reason to try to prove it wrong. What happens next is a completely different kind of challenge. Building factories that can make this hardware cheaply and reliably, agreeing on shared global standards everyone can actually live with, installing all of this equipment across entire cities, not just a single test block set up to impress visiting officials. None of that is really a science problem anymore. It's a massive coordination problem. And coordination problems tend to move a whole lot slower than any single lab breakthrough ever does. There's one more thing worth sitting with before we wrap this up. Every single leap forward in wireless technology throughout history has followed almost the exact same pattern. It shows up first in wealthy cities that already have money to spend on shiny new infrastructure, and it takes years, sometimes decades, to reach the places that could actually use it the most. Rural clinics without a reliable internet connection. Schools in remote areas still waiting on their very first stable connection to the outside world. Emergency response teams working in disaster zones where the cell towers were often the very first thing knocked out. If a network this fast and this capable ever actually makes it all the way out to those places, it stops being just a cool speed record people talk about for a week and then forget. It genuinely changes what becomes possible for the people who need it the most. That's really the bigger story hiding underneath this whole breakthrough. Not just how fast one lab managed to move data through thin air on a controlled test day. Whether the rest of the world actually decides to build on top of it, how fast that happens, and who really ends up benefiting once it's finally real. If this kind of deep dive into the technology quietly shaping your future is something you're into, go ahead and hit that subscribe button and turn on notifications so you don't miss the next one, because there's a lot more of this story still coming. Now, I actually want to hear what you think. Do you believe this kind of network eventually makes it out to rural areas and developing countries within the next 10 years? Or does it stay locked inside a handful of wealthy cities, the same way basically every generation before it has? Drop your answer in the comments. I'm genuinely curious where people land on this one.